Hi, everybody. Today we're doing something really valuable, and that's the derivative and the slope of a graph. This is a huge thing in calculus. So in calculus, one of the things we'll look at is if you have a curve. See here I have like an upside down, looks like a parabola, and I have tangents. There's a tangent line, there's a tangent line, and it's of great interest to know the slope of the tangent line. It'll make a huge difference. So because that kind of represents the instantaneous rate of change. So here we have a line like this, here we have a line like that, here we have a line like that. By the way, notice that this guy over here, this middle case, if I extend the tangent line, it's going to hit the curve again, like over here. And that's okay. It's okay. Normally we think of a tangent and it hits the curve only once. So when we say tangent in the calculus class, we mean at that sort of localized point, only like in this small area, it hits the curve only once. But it's okay if it hits the curve again somewhere else later on. It doesn't matter. It's still considered a tangent as far as we're concerned. Anyway, these are all tangents. And finding the slope of the tangent is going to be extremely useful. As I said, it's going to represent what we call the instantaneous rate of change, among other things. So that's just approximately. So in figure 2.6, so this depicts the average monthly temperature in Fahrenheit in Duluth, Minnesota, which I have to tell you, I've been in Minnesota. It is cold in the winter. Estimate the slope of this graph at the indicated point and give a physical interpretation of the result. Well, the slope from the graph, you could see that the given point falls approximately 28 units for each 2-unit change. Again, this you're kind of eyeballing it here. So the slope is going to be negative 28 over 2 because the y value changes negative 28. It goes down 2 every time the x value goes over 2, which is negative 14, which is a slope of negative 14, which means that it's going to be about negative 14 degrees per month. Meaning each month it's going to be about 14 degrees colder than it was. So this means you can expect the average daily temperatures in November to be about 14 degrees lower than the corresponding temperatures in October, and that's what slope kind of gives you. And now, let's look at some of the math behind the slope. So a slope. So to find the slope of a tangent, it's not so simple. How are you going to do that? So what we do is we look at a line that hits the curve in 2 places. That's called a secant. Just like in geometry, you have tangents and secants. Same thing here. So what is the slope of the secant? Well, the slope of the secant is change in y divided by change in x. So if I have a point here and a point there, it's y2 minus y1 over x2 minus x1, like it always is. But what is y2? Y2 is f of x plus delta. Delta x is the change in x. That's how much x changes. And this y2 minus y1, that's going to be, oh boy, I want you to see the picture. That's going to be f of x plus delta x minus f of x. That's f of x plus delta x. That's f of x. And this distance, that's that distance. Delta x, of course, is the change in x. So the slope of the secant is going to be f of x plus delta x minus f of x over delta x. Now, in case you haven't guessed, calculus, as I've said before, calculus is all about limits. And what we're going to do is look at the limit as delta x approaches 0. When delta x approaches 0, this secant kind of turns into it. Will kind of eventually sort of turn into a tangent. That's the best way I could say it right now. We will be more specific about that, but that's kind of the general idea. So these are all just examples. So this is what happened. This is what I was just talking about. So we start with delta x this big, then we go to delta x that big, then we go to delta x even smaller. Notice I have a secant, another secant. This secant is so close to the curve, you can barely see that it's a secant. And finally, you get down to a tangent. So we're going to look at, drumroll please, the limit as delta x goes to 0. So the slope of the m, which is the slope of the tangent, is going to be the limit as delta x goes to 0 of m secant, of the slope of the secant, which is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Notice that this is one of these limits where when delta x does go to 0, the bottom of the equation, the bottom of the fraction gets very close to 0, and the top of the fraction kind of gets very close to 0 because it gets very close to f of x minus f of x. So as you have, it's like one of these 0 over 0 situations. Nonetheless, with calculus, we're trained in dealing with that sort of thing. So let's find the slope of the graph f of x equals x squared at the point -2, 4. So using that formula that we just had on the page before, we want f of -2 plus delta x minus f of -2 over delta x. That's going to be -2 plus delta x squared, because that's what the f function is in this example, and minus -2 squared. So if I just expand this out, binomial expansion, I get 4 minus 4 delta x plus delta x squared minus 4. The plus 4 and the minus 4 are going to cancel. And I have -4 delta x plus delta x squared over delta x. Now, this is really important. On top, I'm going to factor out the delta x. And I have delta x times this parenthesis here. But the delta x that I factored out is going to cancel with the delta x on the bottom. That's very crucial. And I'm left with this little parenthesis, which is -4 plus delta x. But I'm looking at the limit as delta x goes to 0. Well, as delta x goes to 0, it just becomes -4. So the slope of this tangent at that point is going to be -4 based on this limit. And that is and that's beautiful. So I don't have to start eyeballing it anymore. I could just work out the math, work out the numbers. Alrighty. Let's do another example. Find the slope of the graph f of x equals -2x plus 4. So, well, now in this case, it's kind of interesting because this graph, the slope, doesn't even matter. The slope is always going to be the same. So we want the limit as x goes to 0 of f of x plus delta x minus f of x. So f of x plus delta x is -2 times x plus delta x, because I substituted that in for x in the graph in the function. Plus 4 minus -2x plus 4. When you sort all this out, you get -2x minus 2 delta x plus 4 plus 2x minus 4. So the -2x and the plus 2x cancel. The plus 4 and the minus 4 cancel. I'm just left with 2 delta x over delta x. And the delta x's cancel. We basically have a festival of canceling. Then we're left with -2. So the slope of this is -2. And of course, being a straight line, the slope is -2 the whole way through. So, on a curve, the slope changes at every point. So the slope is going to be different at every point. But in a straight line, the slope is just the same the whole way through. Consistency. Okay, finding a formula for the slope of a graph. So if we want to find the formula for the slope of the graph f of x equals x squared plus 1. We want to find a general formula. Then we want to, in other words, rather than see on the previous problem, or 2 problems ago, I should say, in this problem over here, we looked at the graph x squared and we wanted to find the slope specifically at one point. But we want to do that was example 3. But example 5, we want to sort of broaden this a little bit, and we want to find a general formula for the slope at any point. Then we can if we have a specific point, we just plug that point in. So I'm looking here. The slope of a secant will be f of x plus delta x minus f of x over delta x. That's that formula which you're gonna become in. That's basic. This formula is basically gonna get tattooed in your brain. And the function is the squaring function. It's x squaring plus 1. So I'm taking x plus delta x, squaring it, and adding 1. And I'm subtracting f of x, which is again that function up here, x squared plus 1. So I have here x squared plus 2x delta x plus delta x squared plus 1, and then minus x squared minus 1. So the plus 1 minus 1 cancel, the x squared minus x. Notice that I always have a lot of great cancellation. And it's not a coincidence. It pretty much almost always works out that way, at least with polynomials. Finally, when all the dust settles, I get 2x delta x plus delta x squared. Notice I could factor out a delta x on top, which is crucial, because the delta x that I factor out is going to cancel with the delta x on the bottom, and I'm left with 2x plus delta x. And of course, delta x the limit is that it's delta x never equals 0, but the limit approaches 0 as x, we're looking where the delta x approaches 0. So basically, the limit here is just going to be 2x plus 0, which is 2x. So I have a general formula. If you have any point on this curve, 2x squared plus 1, the slope is just going to be whatever the x value is. It's just going to be double that. It's going to be 2x. So if I'm looking here where x is -1, the slope is going to be -2. If I'm looking over here where x is 2, the slope is going to be 4. And all I got to do is take the x value, double it, and now I have a general formula. Give me any point on this graph, and I'll immediately tell you what the slope is. I'll immediately tell you what the slope is. Okay. Moving on. Okay, so now we're going to talk about we're going to officially define the derivative of a function. The derivative of a function, we write f prime of x. So f of x is the original function. F prime of x is the derivative of the function. So that's the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. That is the definition of a derivative. And this is a derivative which I could then apply to any point. I don't have to take it for a specific point. I can apply this to any point once I figure out the derivative. If it has a derivative, we say the function is differentiable. And this process of finding a derivative, we call that differentiation. So that is the sometimes we use the terminology dy dx. Sometimes we say y prime. Sometimes we say d dx of f of x, d little x of y, f prime of x. Unfortunately, there are many different notations. Why do I say unfortunate? Because it's confusing. You know, you have like all these different ways of saying the same thing. Why don't you just say it one way? Part of the reason for that, I believe, is because calculus was developed independently by different mathematicians in different countries. You had Leibniz, who in Germany, who developed calculus. You had Newton in England, who developed calculus, and they were independent. And this is before the times of telephones or email or anything like that. And so they had different like notation. And I think that's why today we see we sort of preserve all those different notations. So just get used to the fact that all these things plus that all mean the same thing. Anyway, but more importantly than what it's called, let's look at the names. Let's actually do the math. So we want to find the derivative of the function f of x is equal to 3x squared minus 2x. So again, we always go to that basic formula. The limit is x as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And this formula here by now is oh, look at that. This formula by now is tattooed in your brain. Oh, look at that. How did that? This formula by now is tattooed in your brain. And now you just have to apply the actual function. So the function to x plus delta x is 3 times x plus delta x squared minus 2 times x plus delta x. And then minus the f of x, which is 3x squared minus 2x. So we're minusing the whole thing. So this becomes, if I just, expand it all out, FOIL it out, whatever, 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x minus 3x squared plus 2x. Notice that the 3x squared and minus 3x squared cancel. The minus 2x, the plus 2x cancel. That kind of happened. Notice that's been happening all the time very conveniently. And everything and anything and all that's left on top is terms that have delta x's in them, which means I can factor out the delta x on the top. So delta x times 6x plus 3 delta x minus 2. But the delta x that I factored out cancels the delta x on the bottom. I have 6x plus 3 delta x minus 2. Notice that the delta is going to 0, so this middle part is going to disappear. And I finally have 6x minus 2. So the derivative of 3x squared minus 2x is 6x minus 2. And that is awesomely awesome. That is awesomely awesome. And let's do another fun one. Let's do just one. Y is equal to 2 over t. Y is equal to 2 over t. So what's the derivative? So I want to, again, this formula, which is tattooed in our brains, and I want to do 2 over t plus delta t minus 2 over t. Now this is a little tricky. I can't just subtract, from denominators. So I have to combine these fractions into one fraction. So I'm gonna have to multiply, I'm gonna have to combine the two fractions on top. Basically, I multiply the first fraction by t over t, and then I multiply the second fraction by t plus delta t over t plus delta t. And I get on top finally 2t minus 2t plus delta t over t times t plus delta t. All that still over the bottom delta t. Now I can sort of combine this whole thing into the top will stay the same. The tippy top will stay the same, and the bottom becomes delta t times t plus delta t, and that's just a division. That's just dealing with fractions. And by the way, if you're not sure on how any algebra steps happen, well, we will eventually meet each other in class, but you could always call me, text me. We could meet on Zoom, anything, before, well, during this time that we're asynchronous, it doesn't mean we have to be out of touch. We can still, you just always call me, and if there's any steps that you don't get how it works. Anyway, notice that the 2t and the minus 2t cancel, and I have a delta t on top and bottom, which is going to cancel out. And then this delta t here is basically going to go to 0. So I have negative 2 over what it becomes just t squared, because t times t plus 0 is just t squared. So the derivative is negative 2 over t squared, and that's pretty cool and awesome. Okay. Now a function. Hold on a second, please. But now you're probably all celebrating, yay, we can take derivatives of all these functions. Wow, any function I can take a derivative. That's so great. That's so awesome. Well, yes, but not every function is differentiable. For example, over here, the tangent is going to be vertical, and vertical is undefined. Here, there's a discontinuity, so I can't really talk about a slope of a tangent. Like right at the point when x equals 0, it's hard to talk about the slope of a tangent. Here I have sort of like it's a sharp turn. So what would be the tangent through that? The rest of it is fine, but that one point where it's sharp, or this one point over here where it's sharp, what would be the tangent? Would the tangent be like this? Would the tangent be like that? So in order for a function to be differentiable, it has to be continuous at that point. But beyond being continuous, it also has to be what we call smooth. It has to be smooth. You see, because this here is continuous at the origin, but it's not smooth. It comes to a jagged, sharp turn. When it's a jagged, sharp turn, it's hard to define what the slope would be of the tangent at that point. But in order for a function to be differentiable, it has to be continuous, but it also has to be smooth and continuous. And now we have some beautiful homework, it looks like. And here we go, some beautiful, beautiful homework, which I'll assign the problems in Canvas like I always do. And yeah, beautiful homework. And I'm going to give you some problems through Canvas, and it's going to be wonderful. Of course, we'll love it. And that is the story. Well, I want to get back here. I don't want to dwell on that. So bye everybody. It's been loads of fun. Like I say, we'll upload problems on Canvas, and it's been a blast.